Now the power requirement can be estimated by flow produced by the impeller times the kinetic energy per unit volume of the fluid. Now the power consumption of an impeller depends on the measurement of the tank and the impeller baffles. So if there is baffles and if there is unbaffled, the power consumption will be different. It also depends on the liquid viscosity and density, speed of the impeller, and gravitational acceleration, which we will assume to be remaining constant. Now, in the design of mixing and agitation equipment, some standard shape factors are maintained. So, the diameter of the impeller to the diameter of the tank is typically maintained as 1/3. Liquid level and diameter of the tank are maintained to be the same. The baffle width is typically 1/12 of the tank diameter. The clearance from the bottom is 1/3 of the tank diameter. The width of the impeller is typically 1/5 of the impeller diameter, and the length of the impeller is typically 1/4 of the impeller diameter. Now, if the shape factors are ignored, power requirement for an impeller is given by as a function of the rotational speed, diameter of the impeller, viscosity of the fluid, density of the fluid, and gravitational acceleration. Now, by dimensional analysis, we can find a relation by combining the variables to get some dimensionless number. And in doing that, we find an expression 3 dimensionless numbers. And if we take the shape factors as other dimensionless number, so this left side becomes function of this set of dimensionless numbers. Now this dimensionless number here, see that P over N cube over N cube dA5 rho, this is called this power number. And N dA square rho over mu, that's the Reynolds number. And N square dA over G, that's called the Froude number. So we have the relation power number is a function of Reynolds number, Froude number, and the shape factors. Now for Reynolds number, if Reynolds number is less than 10, the flow is laminar. The Reynolds number is greater than 10,000, that's turbulent. And between 10 and 10,000, we have the transition region. Now Froude number appears in fluid dynamic situation where there is significant wave motion. So Froude number is important for ship design. However, it's not important when baffles are used or Reynolds number is less than 300. Now for agitation and mixing, unbaffled vessels are rarely used at high Reynolds number. So Froude number is not included in the correlation of power calculation for mixing equipment. So power number becomes a function of the Reynolds number. And experimental value shows relation between this power number and Reynolds number for different impellers. As you can see in the next figure. So here in this diagram, it shows the relation between power number and Reynolds number for different type of impellers. So this one is for disc turbine, this one is for CD6 turbine, this one is for pitched blade turbine, and these two are specially designed turbine, what is called as A310 and HE3. These have special characteristics in terms of their dimensions and shape. So from this relation, if you know the Reynolds number, you can find the power number for a given impeller. This is another relation for helical ribbon, baffled and unbaffled propeller. For this case, you see here that for when there is baffled, the power number is a little bit higher than the condition when it is unbaffled. Meaning that for baffled vessel, more power will be required. So again, this is the relation between the power number and Reynolds number for specific impellers. So from experimental observations, there are some correlations and there are different observations of the variation of NP with Reynolds number. So these are a few listed here. One important will be for Reynolds number greater than 10,000, so NP remains constant, and for Reynolds number less than 10, NP varies inversely with Reynolds number. So this gives us different formulation for power requirement in laminar and turbulent flow. Now we know that the definition of this power number is P over N squared dA5 rho. Now from here you can calculate the power to be NP N squared dA5. Now if you know the power number, you can calculate the power requirement for given speed or given impeller diameter or given density of the fluid. However, the data on power number may be available for different flow conditions. So when the Reynolds number is less than 10, the flow is considered to be laminar. Now for laminar flow, this power number is inversely proportional to Reynolds number. So that we see on a log-log plot. It's a linear line with a negative slope. So we can write this NP to be some constant KL over RE. So we know that for RE, just a detour, that the general definition of RE or the Reynolds number is dV rho over mu. Here D is taken as the dA or the impeller diameter, and V is taken as the linear velocity of the impeller, which is given as N dA times pi. Now Reynolds number, if you substitute this here, you will get RE to be pi N dA square rho over mu. However, when calculate Reynolds number, pi became a constant. The Reynolds number is defined as RE to be N dA square rho over mu. This pi already is a constant, so you define this dimensionless number as this one. So we have Reynolds number equals N dA squared rho over mu. So if we plug in this into this formulation, we'll get P to be, we have NP to be KL over Reynolds number. So we'll have KL times the inverse of this. It will be mu over N dA squared rho times N squared dA by rho. So this should be N cube. So this should be N cube as well. So we'll have P equals KL N squared dA cube mu. So that's the expression for laminar flow, where this KL data is available for laminar flow conditions. Now if the flow is turbulent, so Reynolds number greater than 10,000, the flow considered to be turbulent. And for turbulent flow, this NP is not a function of Reynolds number. So we can write NP to be a constant KT. So if you simply plug in this equation over here, so P will be KT N cube dA phi rho. The values of KT and KL are available in the literature. So if you know the flow type, you can directly use these two equations. However, if this is the case that you have Reynolds number between 10 and 10 to the power 4, we need to use this equation. So P equals NP N cube dA phi rho. Please do note that for laminar flow, the mu comes into play, and for turbulent flow, the rho comes into play. So there are experimental values for these two terms, KL and KT. Those are available in the literature, and we will extensively use these to calculate the power requirement for different impellers. For example, with a pitch of 1 for propeller with 3 blades, the KL value is 41 and the KT value is 0.32. Do remember that this ratio does not tell anything about the power requirement for laminar turbulent flow because the equations are different.